John Milsom is going to talk to us about Ron Mason and the discovery of magnetic stripes. And it's a story I suspect that not many people are familiar with or don't know much about. So I'm very much looking forward to this. And I'm now going to hand over to you, John. Thank you.
Okay, so Ron Mason and the discovery of magnetic stripes. Um, every geologist, I guess, or perhaps not quite all, would know what these pictures show. It's the magnetic striping of the seafloor to the west of the coast of the United States. But I wonder how many now would know that these lineations were originally called the Raff Mason or Mason Raff lineations, and how many would remember that, and how many people would have even have heard of that. So, Raff Mason, Mason Raff, who were these people? And I never met Raff. He was senior lab technician, later associate engineer at Scripps. And here is how he described himself. He said, "The duties I perform for the laboratory are non-routine and vary greatly from month to month. It must be remembered that my work is of a research nature into new fields where techniques have not been established. This requires persons with considerable originality and adaptability and is not something that can easily be listed as duties performed for the laboratory." So, not the most modest of men, clearly. And as I say, I never actually knew him. I did, however, know Ron Mason rather well, although not till some time later. He was my PhD supervisor from 1968 to 1970. So going back quite a time in his career, in 1952, December 1952, he flew to Suva to join the Capricorn expedition to tow a magnetometer behind. And he was taking a berth that was previously occupied by Raff, who'd been improving the hydrophones. These two were to work together on magnetics for the next 10 years. How did that happen? And um, uh, um, one thing that I did a couple of years ago was, at the request of the Royal Astronomical Society, I wrote a little paper about what I then knew about Ron Mason. And that was what prompted Duncan to ask me to do this. And I didn't want to just rehash what I did for the Royal Astronomical Society. So I delved a lot further back into Ron's past, which was not an easy thing to do. But anyway, there's very little written about him. His Wikipedia page is very, very scanty, and he actually published extraordinarily little. But anyway, he did get a obituary at Imperial College, and that told me he was born in Hampshire in 1916. He went to Eastbourne Grammar School, and then he went to London University, Imperial College, Royal School of Mines, graduated with a physics degree. But like most people born in 1916, just after graduation, his life was to change drastically because World War II was about to begin. And as a scientist, he went into the Royal Electrical and Mechanical Engineers. He worked on perfecting methods, radar methods by which tanks could locate themselves in the featureless desert using a rotating beam. And also, and something I'm sure that he must really have enjoyed because he liked that sort of thing, he worked with a hearing aid firm to make a miniature radio inserted into dartboards and shove halfpenny boards sent to prisoners of war. That he would really have liked because he was, and he would always remain, an instrument man. So 5-6 years in the army. He left the army, went back to the Royal School of Mines, took an MSc in applied geophysics, and in 1947 he was appointed as lecturer in the geophysics section. And it was a good time to be a geophysicist, even if people did make fun of you, as you can see on the right, because the discussions led up to the International Geophysical Year, and one of the notable things about the Geophysical Year was that it was actually 18 months long. Anyway, after 4 years, Ron managed to hook himself a sabbatical at Caltech. Nobody starting their university career now could manage that after 4 years, I'm sure, but I suspect that the IGY was behind it. And he went to Caltech, but while he was there, he attended a meeting at Scripps, the Institution of Oceanography in San Diego. And they would contribute 3 research vessels to the IGI, and they would also be in charge of the IGY's Pacific Island Observatory program. And here is one of their vessels, the RV Spencer F. Baird. And this was the ship that Ron actually went to sea on. And it's important to remember that in 1952, almost nothing was known about the bathymetry of the Pacific, particularly the Eastern Pacific, because although the US Navy had gathered a great deal of information, bathymetric information, it all been over in the West where all the fighting was. And so this was a big blank. And although this map is a Russian map of 1952, and so doesn't show anything that the American Navy knew, it's a pretty good idea of how little was known about the seafloor at that time. And Scripps was doing their best to remedy that by sending research vessels out, equipped with a range of sampling and measuring equipment, but not with magnetometers. That the Baird had a magnetometer at all happened only accidentally as a result of that meeting at Caltech. And I'm going to read to you what Ron himself had to write about it much later. Talking casually to Scripps seismologist Russ Raitt during the morning coffee break, I asked whether anyone had thought of investigating magnetic anomalies associated with seafloor structures by towing a magnetometer behind a ship, an operation that could enable ships to obtain valuable data while engaged in other operations. "What's that?" came a deep voice from behind me. It was Roger Revell, director of Scripps. And after the briefest of explanations, he said, "Well, do you want to do it?" To which I promptly replied, yes, and I became Scripps magnetometer man. And his first task was to look for a magnetometer because Scripps didn't have one. And nobody knew where there was a marine magnetometer. And Ron discovered that Lamont, who was looking after the Atlantic, oceanographically speaking, had actually tried to tow a magnetometer, make transects across the Atlantic, and they'd made 4 attempts and only one had been in any way successful. And they only got around to publishing that a year after this meeting at Caltech. However, Ron discovered it and managed to borrow the magnetometer from Lamont. And it was going to be used on the Capricorn cruise, which was a 2-ship operation. In those days, one of the things that the oceanographers were very keen on was discovering how thick the ocean crust was. And for that, you needed to do seismic refraction. And for that, you needed one ship to let off explosive charges and another ship to record them at distances of tens or sometimes even hundreds of kilometers. And so Ron actually was put on the Baird, which was the receiving vessel, and he actually replaced RAF. He flew out to Suva. So the first part of this cruise he wasn't on. He was only on this rather complicated one through the islands in the South Pacific. He joined at Suva, and so added his magnetometers to the seismic experiments, the echo sounders, samples being obtained using scuba divers, corers, dredges, bottom samplers, temperature gradients being recorded in the sea, hydrographic data recorded, and of course, bathymetric data. All that was being recorded. And here is the instrument being put into the sea, and that is very definitely Ron on the right. And they encountered, of course, the difficulties that Lamont had encountered with the stability of the instrument, and they decided that the fish, the enclosure that it was in, needed considerable redesign. That work was done, and just about they managed to get it towed in a fairly stable manner. And here is a look at the inside. So everything had to go in that little fish. Now, I'm not absolutely sure that this picture is of Ron, although scripts swear that it is. It doesn't look much like him. And we'll see a picture of him later, which shows very much what he was like. So he was on this ship, and what did his colleagues make of him? Well, one very interesting colleague who was on board was the first woman ever to go on a US oceanographic ship. And that was the wife of the chief scientist, Helen Raitt. And she wasn't supposed to be on it, but being an enterprising woman, she used to track the ship so that she flew to Suva and was there when the Baird arrived there. She then got a boat to Tonga. And in Tonga, one of the scientists had to leave in a hurry. And there was only one berth on the boat going out. And if he'd missed that, he'd have to wait another month. So a deal was done. Helen took over his cabin on the Baird, and John Isaacs disappeared. And after she came back, she wrote a book called Exploring the Deep. And she didn't have much to say about Ron, but she described him as our Englishman who usually turns up in the lab about midnight to work on his magnetometer records. He is a lone wolf, working late at night when there's more space on which to spread out a 23-foot-long record. The only other mention she makes of him is that one night he asked me just about 12 o'clock, "Helen, are you hungry?" "Yes." "What'll you have? Sardines, apple, eggs?" And he pulled 3 hard-boiled eggs out of his pocket. Very characteristic of Ron, but really, would you want to eat a hard-boiled egg that had been in his pocket for goodness knows how long? Anyway, I think Helen got him right in one respect, certainly lone, but a wolf, nothing could be less vulpine, I think, than Ron. But I very much like this picture of the scientific crew of the Baird just as they were coming back to San Diego. And there is a nice row at the back, a row at the front, and there is Ron in the middle forming a row of his own. A loner, very definitely. So anyway, what happened on Baird? Well, it was actually technically a fantastic success where Lamont had failed to get even more than one continuous profile across the Atlantic. Ron managed to get nearly 8,000 miles of record, a technical achievement of a magnitude that cannot be overstated. But the main lesson that was learned from that was actually little point in gathering magnetic data along long isolated lines. You can see that at the bottom here. 2 profiles. One is the magnetic, the lower one is the bathymetry. There is some correlation. Over on the right, there is magnetic anomalies that's going through the Society Islands, Tahiti and Bora Bora. However, there are places where there is a bathymetric high and no obvious correlation. Plenty of places where they have magnetics. and no bathymetric correlation. What do we make of those? You can't make anything of them because you don't know what was going on out to the side. So it's the sort of thing that might actually have made people decide not to bother with magnetics at sea. However, they did do a couple actually of what you could call magnetic surveys, which were a bit more interesting. And this is the largest of them, so none of them very big. And this was round Palmerston Atoll. And in the cruise report, Ron provided a commentary on this. And he said, amongst other things, there's a large positive anomaly off to the northwest side. And the geometrical relationship of the total field and bathymetry points to the existence of a basin in the underlying igneous rock on this side of the atoll. Now, one thing that comment shows is that Ron at that stage did not actually have the first idea of what magnetic anomalies looked like. And this was at a time, it's 1952 now, and actually aeromagnetic surveys for geological purposes were already pretty well established in the States and in Australia. And what they had not revealed, because they expected it, was the fact that magnetic anomalies are never single anomalies. They're always in two parts because magnetics always has a positive and a negative pole, or a north and a south pole. And so what happens is, here is a little picture. So the Earth's field magnetizes this, it produces a secondary magnetic field, and over to the left at A and B, in fact, the magnetic field that produced by the body is actually opposed to the Earth's field. So that comes out as a magnetic low. And immediately over the body, you're getting into the region where is the gradient between the high and the low. And then it's only when you get over to D that you actually get positive anomaly produced by this positively magnetized body. And just to prove I'm not making this up, here is a magnetic map from something at the same latitude, roughly the same latitude that the Palmerston survey was at. And it shows a very beautiful dipolar anomaly from a singly magnetized, uniformly magnetized volcanic plug in Papua New Guinea. So Ron at that stage didn't even know what a magnetic anomaly should look like. Anyway, he collected a great deal of data, and among other things that they collected on the bed was very long piston cores. And he got interested in the magnetization of these. And after he got back to Scripps, he got together with Rath, and the two of them collected piston cores in red clays east of Mexico. And he took the samples back to London to analyze them. And unfortunately, core tops were usually missing. And he tried to correlate one core to another using the magnetic signature. And he found it worked. And he thought that this was proof of field reversals. And he actually wrote a little paper about it, which he circulated amongst the oceanographers and geophysicists at Scripps. And one of them said, well, good idea, but you'd look like a fool if you published it. And so he didn't. Now, I regard this as an absolutely seminal moment in Ron's career. When he took me on as a PhD student, which was an accident anyway, and I arrived having worked in Australia for 6 years with a complete set of data for a PhD from Papua New Guinea. And his only comment really to me when I arrived unexpectedly, because the man who was going to supervise me had died, was, oh, New Guinea, risky place to be working in geology at the moment, because you could be proved wrong in anything you say in a few years' time. Ron had an almost pathological fear of being proved wrong, and that led to him having an extraordinarily small publication list, and also having very little of interpretation in what he did publish, which was a great pity, because what he published was something very, very interesting from this area. So there's Vancouver Island up there, San Diego down here. This is the same map, the 1952 map, no feature at all in that. Now, the US Navy and indeed Scripps knew that there were fracture zones in this area, but they hadn't been defined. And the US Navy desperately needed to know the topography of that area, because they were interested in what submarines could and couldn't do in them, and communicating with submarines and so forth. And so they installed a magnetometer on this ship, the Pioneer. And when I was at Imperial, the rumor was that it was Ron who had insisted on the lines being parallel and a really regular survey and being done and so forth. But in fact, that was complete hogwash. The regular lines and the regular pattern were entirely due to the Navy. And Menard described what really happened, and he said, the Pioneer surveys, no more serendipitous relation can be imagined than the needs of the Navy and the discovery of magnetic stripes off the west coast of North America. Navy wanted to deploy a new, very long-range listening system, and they had to know the location and size of every seamount and fracture zone. And Scripps was asked about it because of their research on fracture zones and physiographic province in the area. And Menard went to talk to them in Washington. And just as he was leaving, he was asked if there was anything else the ship could do that wouldn't interfere with running straight sounding lines in a regular pattern. And he remembered Capricorn. Ron was still working on his red clay cores, and suggested a magnetometer. So you think, everyone said, yeah, great idea. Let's put a magnetometer on board. No way. No one in the Office of Naval Research or any of its advisors could see any point in towing a magnetometer on the Pioneer survey. The USGS, it'd be a waste of money, or refused to fund it. And thus it was, again, Roger Revell, one of the most significant geophysical surveys, only got done because Roger Revell was prepared to put his very small personal research grant money that he got as director of Scripps into putting a magnetometer onto the Pioneer surveys. So they started, actually a little bit late. They didn't get in on immediately. But then once they'd started, magnetic data started to pour in, and Ron began to analysis, which was to continue for years as his colleagues grew increasingly impatient. And Revell particularly was obviously getting very worried because he spent all this money, which everybody had told him was going to be wasted, getting this magnetometer on the Pioneer. And it seemed as though it might be a complete waste of money. But when Ron actually produced maps, and he produced a map just for the first survey, which is the one shown here, people realized it hadn't been a waste of money, and something very, very odd was happening out at sea. Why was it all taking so long? Why didn't they just look at it? Why didn't they just look at a plot like this and say, oh yeah, we can see all these linear anomalies on what we would call a stack profile section. We didn't need the contour maps. Now, this is a very late profile of survey over the Carlsberg Bridge. And by that time, people knew a lot more about the Earth's magnetic field, and particularly what one might call the baseline should be in those areas. And they also had better means of communicating with the ship, and so communicating what the Earth's background field was doing, because it varies from day to day. Ron didn't have anything like that. He didn't know what the baseline should be. He didn't know what the Earth's magnetic field was doing. And so, as Menard put it, he had to plot thousands of magnetic observations along the ship's track, had no datum, magnetic field not known in sufficient detail. So what he did was he calculated a moving average and subtracted it from the observations. And this was his major contribution, really. And it was a very tedious, but again, he was a man who liked detailed work. He liked doing tedious things and doing them with high precision. Now, a running mean means that you take a certain number of points along line, average them, and point that plot as the value at the middle. It is, in fact, a form of filter, both high pass and low pass, according to the length of the number of points that you choose to use. And Ron presumably did a lot of tests before he actually settled on something, but at any rate, he picked exactly the right length for his filter to show up all these linear anomalies. And this was just from the first survey. And much to my surprise, when I was writing the Royal Astronomical Society paper, he published it in 1958. Now, if you read almost all the literature on this, you'll say that the Raff-Mason lineaments were first published in 1961. They weren't. They were published in the first issue of the Geophysical Journal of the Royal Astronomical Society, now the Geophysical Journal International. They were published then, and they attracted almost no notice whatsoever, except with the people who knew about it even years before, the people at Scripps. And so Ron published that, and here are some extracts from his publication. He went to a company that was already doing airborne magnetic surveys to get their opinion of what he was getting. And they came back with, it's our opinion that such a high value of susceptibility may be indicative of appreciable remnant magnetization, that is permanent magnetization of the slabs. Okay, so he'd been told by people who knew what magnetic anomalies should be looked like that this pattern showed remnant magnetization. And the airborne boys also drew attention to the fact that the north-south anomalies appear to have two maximum in some cases with an intervening minimum, and suggested the lines of minimum field might have some structural significance. It's worth pointing out at this stage that the fact that the lineations and the anomalies run north-south, that wasn't a feature of the original planning. Nobody said, well, we think the anomalies are going to run north-south, we're going to run east-west lines. East-west lines were run because they thought the bathymetry might run in that direction. But it was very important because the anomalies showed up beautifully because the causative bodies were oriented north-south. Anyway, another thing that Ron knew was that paleomagnetic measurements, and he quoted Runcorn on this, suggests that since Jurassic times, the direction of the Earth's magnetic field in North America has centered around a dipole field with normal or reverse polarity. And then the final kicker However, it seems clear that since any remnant magnetization is required to augment rather than to oppose the present field, the vertical component must be substantially downwards, and this makes any appreciable degree of reverse magnetization unlikely if the magnetic poles were anywhere near their present position. I've read that again and again and again. I feel like screaming, Ron, 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 you've got it all. It's there in your hand. The reverse magnetization is not unlikely. It's what you're looking at. And as he later said, he could have kicked himself for not knowing about it. He said, and one reason he didn't pick up on it was that he was diverted. He went, Scripps, he was their magnetic man, and they needed someone to supervise the setting up of magnetic observatories in the Pacific. And Ron left RAF to take care of the remainder of the field seasons and so forth, and went and did this work on magnetic observatories. It's resulted in one of his very, very few publications. But as he was to say later, I was familiar with ideas about seafloor spreading and with reversals of Earth's magnetic field. I could have kicked myself for not thinking of the idea. Well, of course, other people did eventually, but not on the basis of the 1958 paper. It wasn't until 1961 when the full suite of anomalies going right up to the Canadian border had been established that people started thinking about that. And by that time, in 1961, also, Dietz had published his ideas on seafloor spreading, and Hess had beaten him, but in an unpublished report by a short margin. So seafloor spreading was out there, and his Dietz's paper was seen by Morley, who already a Canadian geophysicist, and he realized that seafloor spreading might account for magnetic patterns in which Mason and Raff had observed, submitted a paper to Nature in February 63, but it may have been thought too speculative. This is Richard Howarth in his recent Jolsock memoir, History of Geophysics, says it may have been thought too speculative or was reviewed by someone at Cambridge as it was rejected. I think that's actually slanderous or libelous, because what Richard is actually saying there is that Cambridge rejected it not because they didn't agree with it, but because they did agree with it. He's suggesting that either they got the idea from the paper and decided to reject it and publish their own, and I don't believe that. But I do think there is a possibility that they were about to publish their own conclusions based on work they'd done on the Carlsberg Ridge, and they didn't want Morley ahead of them. We will never know, but that is clearly what Howarth is suggesting there. Anyway, publication was finally achieved in Nature in September 1963 with Vine and Matthews' Magnetic Anomalies over Ocean Ridges. And according to Fred Vine, it was submitted in late June or early July of that year. And that essentially is the end of the story. But of course, it's not the end of Ron's life. What did Ron do after having missed that? Well, he went back to the Royal School of Mines and he found another research project to work on that suited him down to the ground. And that was to go to Iceland and to set up very securely mounted pillars on either side of the Reykjanes Ridge onshore and measure very, very precisely with an instrument called a machometer the distance between them. And the micrometer could give him distances of kilometers to accuracies of a centimeter. But of course, nothing would show up. You couldn't sort of do that work and expect to have anything publishable. You had to wait for a few years to see if those pillars that you set up had moved apart. So from Ron's point of view, a very nice project, lots of data to work on, a lot of interesting instrumentation to work with, and publication almost assured in one way or another, but you didn't have to publish anything for 4 or 5 years because you could say, we haven't got the second round of results in. So they got the second round of results in and showed about 9 millimeters per year of extension. And he went on later and did the same sort of thing in the Imperial Valley in California. And so that was the thing that he published mainly on after he left Scripps, gone back to RSM, joined Magna. And one thing I will say for him, he was not a hogger of the limelight. Brander and Calvert, and Brander, the lead author, were his research students. Ron was not one of those supervisors who wants to be first author of their students' papers. He was quite content to be second. And as I say, that is really the end of Ron's story as far as magnetics and stripes is concerned. And as a man, he was always something of an outsider, someone on the edge of things somehow. And there he is again, another picture from Scripps as she the bed as she steamed back into San Diego. And there on the far left is Ron, again, forming a separate line and somehow not quite in the picture. And there, from there, he went back to the Royal School of Mines and taught there, became professor, head of the geophysics department until his retirement. And that's it.
Thank you, John. That's
right. Can you still hear me, Doug?
I can.
Duncan?
Thank you very much indeed.
I thought I'd managed to leave a certain time for anybody to come back with questions or.
Well, that was absolutely fascinating in a range of ways. I've just brought everybody up on screen so we can perhaps have if anybody got questions or points that they want to make, they can do so. I've got one comment that I'll put forward, but I'll give other people a chance first of all. So if you wish to say something, just sort of open up, and I can see one or two people opened up already, and unmute at the bottom of your screen using the toolbar, and we can ask John those questions. Is there anybody got anything that they want to ask or comment on? Brian.
Can you hear me okay?
We can, yes. Good to see
you.
Can
you elucidate for me, because when this was coming up and I was an undergraduate, in the night when the plate tectonics or so on was starting to, I had it in my mind that Harry Hess discovered these stripes. I mean, I know he discovered, if you like the right word, is geos, but how did he come into the general, shall we say, plethora of data being associated at this time? Where did Harry Hess come into this?
He wasn't one of the leaders. He was further up the food chain. He was more the Roger Revelle man. Although Revelle, I always feel Revelle he's hardly mentioned. But he was the great facilitator. But Hess was also one of the gang there who was, and they were all working together on it. But as far as I can find out, he was not one of the major movers and shakers in this particular story. If anything, he came in rather later.
Okay, because as I understood it, and this is going back years and years ago when I did some extramural things at Manchester before I went to university, it was said that Harry Hess, and I think it was supposed to be in a destroyer, not as a submarine on the screen, was towing a magnetometer when he was going backwards and forwards in a troop ship over the Pacific. And picked up at least some of this information then, but maybe I've just got that wrong in the depths of my befuddled mind as an undergraduate.
He would certainly have known about the. I think, although I haven't actually checked right through, because Scripps had so many ships and so that, and I think they probably only had one magnetometer, but they certainly continued to do magnetic work. Until then, the magnetometer had to go on to the Pioneer to get the data for the Navy. So again, I have to say, one of the interesting things is that Lamont. One thing about Lamont was that it was a hotbed of no continental drift. They were actually fairly resistant. If you read, and I think someone's going to talk about Mary Tharp and so forth, and she, of course, was at Lamont, and she nearly got sacked for indicating continental drift might be possible. Scripps people were much more open, but what they were interested in, and what they started to use the magnetic stripes for, was to try and work out the offset on the big fracture zones. They didn't exactly. Nobody asked what's causing this. Interesting. We can probably work out how big an offset there is on the big fracture zones. Very interesting sort of tunnel vision, I think.
Very interesting. Very
okay. Interesting. Thank you. Yeah.
Yes. Well, it's interesting. In one sense, I wonder whether it is tunnel vision or whether it's that they. You're right. They obviously didn't have the vision, but it's easy to have the vision with hindsight than to think it is with foresight. So in that sense, I'm probably a bit more forgiving. But maybe as a data man, you probably think that they should have seen some of this much more obviously than they did.
No, not necessarily. I can really understand it because they'd already got a project going, and this was suddenly a bunch of data, which was going to tell them something about their project.
Right.
And I can well understand them seizing upon it and saying, yeah, we can use this, and not bothering too much about any other implications.
Yeah. And it is interesting, isn't it? That's an interesting point, isn't it? That we in terms of science generally, that often data tends to be applied to a project which is already thought about and goals that have already been thought about, rather than it being something which it might lie outside that, because we perhaps don't think beyond that. And it seems to me that occasionally the scientific breakthroughs are from when somebody has sort of looked outside the sort of the project tunnel, as you would have it. Yeah, very interesting.
Yeah, if I could come back on that, I would say one of my thing I'm rather proud of is that I am the first person to have noted that the Woodlark Basin was a young spreading centre and so forth. And I did that because I was making terrain corrections for gravity surveys, and for that I needed to get the bathymetry. And right. I got it from the Australian Navy Hydrographic Office, and nobody had looked at it in bathymetric geological terms till then. I looked at it and thought, that's the bloody fracture zone.
Right.
And
right.
It's all too easy to get just focused on what you're doing, and anything is grist to that particular mill.
Yeah. Yes. Thinking out of the box can sometimes give big rewards. Quite often not, though, and I think that's obviously the risk. And
that's also very true.
And well, it's interesting, isn't it, in that that in one sense was the comment, the advice given to Ron Mason. You're going to look very foolish if you publish it, because he probably was beginning to think a little bit out of the box, but then retracted back inside it.
Yeah, I think that was a seminal moment in Ron's life. He was quite a nervous guy, and not terribly sure of himself. I mean, it was legendary in the department when I was there that you never knew whether Ron was in the department or not, because his door was always shut and locked, and you didn't know if he was inside it or not.
Right. Interesting.
And so he was quite a timid man. I can imagine at that stage, as a fairly young researcher, he was a very, very timid man. And for someone to tell him, "Oh, you'd be laughed to scorn if you did that," he'd come up with the right answer.
Yeah.
And someone kicked him in the teeth.
Yeah.
And appalling, really.
And it's interesting how the trajectories of history and science history, or they go down a different trajectory as a result of sort of these quite small ripples, in one sense, which fade out rather than actually grow bigger. I'm not sure I've quite got my analogy right there, but I'm sure you understand what I'm saying. Quite interesting, I think.
Oh, I do. I'm a great fan of Hooke, who I think Newton really was the also ran in that, who just did the numbers. But I think the ideas man at the time was Hooke.
Yeah, interesting, very interesting. Can if I can ask a question? I mean, unless there's somebody else who's keen to get in or make a point, it's actually a slightly bigger point, I think, from what you were suggesting about how magnetic stripes, our understanding of magnetic stripes came along, and how that contributed to really the development and acceptance and understanding of plate tectonic theory. In the lecture that was recently at the Royal Institution, which I listened to online by Naomi Oreskes, the thesis of her talk was that she was claiming that plate tectonics was understood before World War II. Now, what's interesting is that there was a question, the very first question she was asked during the discussion was somebody who raised and said, well, is it really was that the case? Because isn't it that science follows the development of instrumentation? And in your case, it's the development of and application of being able to the confidence of magnetometers, which led to all the data that Ron Mason collected and then subsequently others collected. And then, of course, that interpretation, which then helped understand, give that confirmatory evidence in terms of seafloor spreading, and then, of course, related to plate tectonics with the anomalies. So it strikes me that this particular story almost demonstrates that it is the instrumentation that you've got to develop first, and that the science, in one sense, follows, at least a detailed understanding of the science follows that instrumentation. I wonder if you've got comment on that.
Yeah, well, as far as the rest is concerned, I said in the blog, I think she's too young. She wasn't there at the time, so she doesn't know the sort of feeling there was and so forth. When I was having geology force-fed to me at RSM, because I have a physics degree, it was still Weus Holmes, who was, of course, a fan of continental drift. But Oreskes doesn't seem to even understand the difference between believing in continental drift and believing in plate tectonics. There are lots of people who were believing in continental drift. And in fact, when I went out to Australia, which was my first job, 1961, I discovered that everyone in the Southern Hemisphere believed in continental drift because they couldn't explain the faunal relationships between Australia, South America, Antarctica, South Africa, and so forth. But the idea of seafloor spreading, if you like, came from Hess and from Dietz really, who published it. And going back, I mean, Hess did publish, but not, or he didn't publish. It was an internal report. And Dietz was the man who published seafloor spreading, and he didn't know about the previous internal report. So I think they both get credit for that. But anyway, and in the Southern Hemisphere, people come up with all sorts of explanations, like Sam Carey in Tasmania was talking about expanding Earth to explain, the continents drifted apart because the Earth expanded, because G changed, the gravitational constant changed. A really way out theory, but a lot of people subscribed to it then. And so the plate tectonics idea really did come with seafloor spreading, and seafloor spreading would never have been more than a nice idea without the magnetic stripes. I think that's probably the way that you have to look at it.
Yeah, and it, just going back to my point that you couldn't really have detected those magnetic stripes without the magnetometer being developed. So in one sense, the plate tectonic theory could not really have been understood, certainly not in the terms which it became convincing pre-World War II, because the magnetometers, it was Ron Mason who really sort of developed the reasonable magnetometer, or magnetometer that would give a reasonable quality of data.
Well, he worked on the fish more than that, but it's Mathieu, who was also at Scripps, was the man who actually developed the magnetometer, and of course he did it for anti-submarine work in the Second World War.
Right. Okay. Two other people, please. Betty Higgs first, and then Tim Carter.
Betty. Thanks, John and Duncan. I just wanted to add to that question Duncan asked. In my understanding of plate tectonics and study since, I would say that the hypotheses come first. So people see what's happening, they observe, and then the instrumentation provides the theory. So you have the hypothesis, and then you have data that proves the hypothesis and creates a theory. And really reading Alfred Wegener's original works, he saw plate tectonics. He wasn't totally correct, but he described, the sort of CMA and CL type story and the breaking apart and the drifting. He was pretty much almost there, but he didn't have those terms and he didn't have the data, all of the data that you had lately. But then, of course, Runcorn kind of provided the data that showed that continental drift had happened, and then obviously with the seafloor spreading, then the magnetic stripes provided the data that then proved them. So I always see it as people have a hypothesis of what's happening and the model's tested, and then they're shown to be right. So the instrumentation is obviously important, but I don't think it comes first.
I think that obviously magnetic stripes is only one of the, but if it had been just on its own, no one would have interpreted it in that way. I tend to think of scientific advances as a sort of, it's a bit like a balance, and you keep on adding bits and bits and bits, and suddenly a final bit goes in and the whole thing swings in the other direction. And the magnetic stripes were, if you like, that bit.
And it wouldn't have happened without Marie Tharp's work.
But I do wonder how long it would have taken if there hadn't been those magnetic stripes. I do wonder if we would, because Marie Tharp got rubbished for even suggesting there was a rift valley down the middle of the Atlantic. Dietz's paper would have been out there in the literature, but again, it would just been one idea amongst many ideas. You really needed some stonking great piece of information, and to come in and suddenly. What it did do was knock out an awful lot of the naysayers, all the people who said it was impossible. You could come back to them and say, well, how do you explain this then?
Very interesting. It's I'm just noticing on Dominic Davey in your background, you have this wonderful oceanographic map behind you. So thank you very much indeed for reminding us of that. And I mean, I'll come to you in a minute, Tim. But it's very interesting in terms of, I think, in terms of how these things were put together. The Marie Thorpe story is quite interesting, and we're going to hear a little bit more of it and some other interesting insights into that, I think, after our AGM, when we've got James Cheshire, who's been and looked at the archive, particularly the archive between her and Heason, and they taped apparently all their, and it's all transcribed, and some of it never been looked at, but he has looked at some of it that's not previously looked at, and we're going to hear a little bit about that in November. So that's very good. Tim Carter.
Yeah, I haven't really got a question, just a little anecdote about the Downing Street divide in Cambridge in 1963-4, when I was an undergraduate doing some geology then. That one side of Downing Street was incredibly excited about ocean floor spreading and plate tectonics, and it was absolutely forbidden for it to be mentioned within the geology department on the other side of the street.
Very interesting.
Yeah, that is a common experience of geophysicists. Actually, I'm trying to write a paper at the moment, which basically is built around the fact that there's some lovely geology work done there, but it doesn't agree with the geophysics.
Can I ask Tim, who was on the other side of the of Downing Street?
We'd heard about Vine and so on, and his work. And
okay, so it was the geophysics people, was it?
Yeah, as undergraduates, we were discussing it, and we were busily being taught about geosynclines and everything else.
Right.
On the geology side.
Okay. Yeah. I think
one of the factors is that marine geology, there were very, very few marine geologists at that time. All geologists almost worked on continents. And so they weren't very clear on what was going on in the oceans, and a lot of them weren't interested in what was going on in the oceans. I just had an interesting to me point about Cambridge is that in 1961, with a physics degree, I went actually to an interview at Cambridge for a PhD post. And I don't know whether I'd have got it or not, because I think it was probably the particular research student that was put in charge of me to show me around the department. But what they were doing there seemed so boring compared with going out and do the sort of things that Royal School of Mines was doing about exploring for ore deposits, exploring for water, exploring for oil and so forth. That all seemed much more exciting than doing research at Cambridge.
Your comment about Ron Mason, about that he enjoyed doing the tedious, he would probably fitted quite well by the sounds of it in the Cambridge crowd.
Yes,
but
it might have been.
That's perhaps the irony, but it wasn't to be. Well, I mean, what a fascinating talk, and it's certainly given us, I think, as a perspective which I didn't really fully appreciate. I sort of vaguely knew something about it, but not really in the sort of depth which you have shed the light on it. And I'm very grateful to you, certainly on a personal basis, but I'm sure that's true for everybody here. So I'd just like to say thank you very much indeed, John, for your talk. Well, thanks ever so much, everybody, and I hope you've enjoyed it this afternoon. I certainly have. And I'd like to thank particularly John, who is in Croatia. Bye-bye now. Have a good afternoon.